All right, class. Good afternoon. This is a great afternoon for me after winning the meme wars. A perfect end note to go out on before spring break. So this is the CHL April 3rd lesson. Hey, James. Hey, Rourke. So today, hey, Rowan. Hey, Steven. Hey, Luigi. Hey, Justin. So we first started off by talking about RC circuits. We covered that. Boom. Then we talked about RL circuits. Boom. Hey, Zach. Today, a circuit that looks like this. You've got an inductor, which has an inductance L, and you have a capacitor, which has a capacitance C. Okay. So we're going to go ahead and solve this circuit. So I'm going to define a current as flowing through the circuit. So I'll call that I. And once I define my current, then I can define the positive side of each element. So here's the positive. All right. So now what I'll do is I'll go ahead and do the a Kirchoff's voltage law loop around this circuit. So I have 0 equals. And first I'm going to go through the inductor. So the voltage drop across the inductor is L di dt. And then I continue around my loop and I arrive at the capacitor. And the voltage across a capacitor is Q over C. If you recall, the main formula for a capacitor is Q equals CV. So this is Q over C. All right. I'm going to take both sides and divide by L. So I have 0 equals di dt plus Q over LC. And then I'm going to take the derivative of this equation. So if I took the derivative, LC and C are just constants, so they don't have a derivative. And so I get the second derivative of I. Okay. Plus 1 over LC times dq dt, like that. You might recall that dq dt is equal, that's the rate of charge flow, which is just the current. So the equation that that describes the LC circuit is d2i dt squared plus 1 over LC times I equals 0. All right. Let's compare that to the equation for it. So I'll count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. This is the equation of simple harmonic motion, because you might recall that the equation of simple harmonic motion was d2x dt squared plus omega squared. That means that the solution is I of t equals a cosine of omega t plus phi. Current undergoes simple harmonic motion. So the current, basically when the current is positive, it's going around one way, and when it's negative, it's going around the other way. So the current kind of like sloshes around. It kind of goes like that. Okay. By comparison, we can see that omega squared is equal to 1 over LC. Okay. Taking the square root says omega equals square root of 1 over LC. All right. And you 2 pi times square root of LC. So that is our equation for today. The period of an LC circuit is 2 pi square root of LC. So if I have the current as a function of time, it looks like this. Simple harmonic motion. The amplitude of the current depends on, hey Aisha, the amplitude of the current depends on the initial charge on the capacitor, basically. Now, one thing I want to say is that I mentioned yesterday how inductors always have a resistance in reality, because the inductor involves a lot of wiring. So, and wires intrinsically have resistance. So really, this circuit is not just an LC. In reality, it's what's called an RLC circuit. And if you want to know the mathematics behind an RLC circuit, it's the same as the mathematics behind damped simple harmonic motion. But I will ask you to look it up. Yeah, I'll show the equation. So what do you think the current would look like if we included the effects of resistance? I'm going to count to 5 for this one. 1, 2, 3, 4, 5. AWOL, how dare you be late to my lesson? So maybe some of you guessed that if we include the effects of the resistance, the current will actually decay to 0. It'll do one of these things. All right. I don't even think you can see that. Let me draw it in solid. It'll do that. Okay. RLC circuits are not on the AP exam, so don't even, if you don't want to look it up, don't. So really that's my lesson for today. It's a short and sweet lesson. I hope you guys have a great spring break, and I will talk to you on Discord after I finish my other 2 lessons. Have a good day. Bye.